Welcome. This course explores the anatomy of an LLM loop, a modular system where code and model intelligence work together.
At a high level, the loop has four main organs: trigger, generator, environment or tools, and evaluator.
A linear path goes input, model, output once. A closed loop keeps cycling until verification succeeds. Think of a thermostat. It reads temperature, acts, then checks again until conditions are optimal. State is the memory core that keeps context history, variables, and step count as the loop turns. Messages travel sequentially through the nodes, usually in a clockwise flow around the loop.
Outside is deterministic code control. Inside is the non-deterministic LLM brain. The loop needs both.
React means reasoning plus acting. The model plans, then acts, then continues the cycle. Section 1 takeaways. Loops combine code and LLM intelligence. State preserves memory, and runs stop only on explicit exit conditions. Pause here. An LLM loop is more than one model call, and state keeps it coherent. Now the quick check. Quick check after Section 1. Which component maintains history and variables across loop iterations? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 2 covers triggers, state, and memory storage that keep a loop running. A trigger can be an API call, a user prompt, or a scheduled job. It launches the loop runtime. State often begins as a dictionary with the user goal, steps taken set to 0, and an empty memory list. Short-term memory lives in the context window, where new observations are appended dynamically. Long-term vector memory can retrieve past experiences with semantic search and inject them into the current state.
In long loops, old observations are summarized or pruned so the context window does not overflow.
State mutates as work completes. For example, steps taken can increment from 0 to 1 after the first node. Checkpointing saves state snapshots, so a loop can recover if a server crashes.
Section 2 takeaways. Triggers start the cycle. State tracks history and variables, and pruning keeps memory manageable.
Pause here. Triggers start the run, and state remembers what happened. Now, the quick check. Quick check after Section 2. What initiates the loop cycle? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 3 focuses on the generator node, the LLM brain that processes state and plans the next move. The generator prompt combines system instructions, state memory, and allowed tool specs into one bundle. Function calling asks the model for structured JSON instead of free-form conversation. In the reasoning phase, the model may think, I need to look up current stock prices using the search tool.
Then the generator selects a tool such as web search and constructs a payload with the query. For complex goals, the generator can decompose work into an ordered queue of subtasks. For reliable tool call syntax, the generator often uses a low temperature, such as 0. If JSON is malformed, the parser catches it, and the schema error is injected so the model can regenerate a valid payload.
Section 3 Takeaways. The generator reads state and rules, outputs structured tool calls, and turns goals into substeps.
Pause here. The generator plans from state and uses structured JSON for reliable actions. Now the quick check. Quick check after Section 3. What is the main responsibility of the generator node? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 4 covers the action node, which executes tools such as APIs, code runners, databases, and browsers.
A dispatcher reads the JSON tool request from the generator and routes it to the matching execution tool.
One common action is an API call, such as requesting weather data and receiving JSON back. A code interpreter runs Python inside a secure, isolated sandbox. Database actions generate SQL, fetch rows, and capture the raw output stream. Raw tool outputs are converted into structured observation objects for later reasoning. Tools can fail, for example with an API timeout. Those failures must become useful feedback. Sensitive actions can pause for human approval, such as confirming a payment before continuing. Section 4 Takeaways. The action node executes tools, sandboxes isolate risk, and results become observations. Pause here. Actions happen outside the model, and observations return to state. Now, the quick check. Pause here. Actions happen outside the model, and observations return to state. Now, the quick check.
Quick check after Section 4. What does the action node do? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 5 covers the evaluator node and termination controls that decide whether the loop continues or stops. The evaluator examines current state and the last observation to decide loop again or terminate. Deterministic evaluators use code assertions, such as requiring code status to equal pass. An LLM as a judge evaluator grades output quality against a rubric, for example, from 1 to 10. On success, the stop signal sets exit loop to true and passes the final result to the user. A maximum iterations guardrail, such as 5 steps, forces a safety stop to prevent infinite runs. Budget guardrails can stop the loop when cost exceeds a threshold and return a graceful fallback.
Decision routing sends failed checks back to the generator or exits on the green success path.
Section 5 takeaways. The evaluator decides continue or stop, using code or LLM judgment, with hard guardrails. Pause here. Evaluators control termination, and guardrails stop runaway loops. Now the quick check. Quick check after Section 5. Why are maximum iteration limits essential in loops? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 6 walks through an end-to-end loop simulation and key production practices. Turn 1, the user asks for a stock price and 10% tax. The trigger creates state, and the generator chooses search.
Turn 1. The user asks for a stock price and 10% tax. The trigger creates state, and the generator chooses search.
The search tool returns $100. The evaluator sees the goal is incomplete, so the loop continues. Turn 2. State includes $100, and the generator chooses a calculator to compute 10% tax. The calculator returns $10. All steps are complete, so the evaluator exits the loop. Finally, the system formats a concise answer. Stock price is 100, and tax is 10. Production loops need security guardrails that sanitize inputs and outputs before execution.
Observability tools log every loop step for auditing and debugging.
Section 6 takeaways. End-to-end loops handle multi-step logic. Observability logs each turn, and frameworks simplify stateful agents. Pause here. A full loop has clear turns, and guardrails plus logs make it production ready. Now the final section check. Quick check after Section 6. What role does the evaluator node perform? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. You completed a quick check after every section. You can now explain the organs of an LLM loop and how they work together.
Congratulations! You completed Anatomy of an LLM Loop. Thanks for watching.